Well, hello again, and in this video I'd just like to take you through the various design phases of designing a buck converter. Typical standard buck converter which we're commonly using as an example in these videos. Okay, so we're going to base this design example on the digital power training kit from Texas Instruments. The kit is a dual buck converter, and we'll just use one of the buck converters in this case to give an example of how to go through the design of the digital power control of this buck converter. Here's the schematic, and we can see here it's a synchronous buck converter. Though the control is only to the main switch, the drivers are doing the synchronous drive. Okay, we have a current measurement of the inductor current and the output voltage measurement here. The output voltage measurement is here, and we can see that it's going to in here, which is channel 6 of the ADC. The current measurement is going to channels 1, which is a slower measurement, and channel 2 of the ADC, a faster measurement there. There's no capacitance. Okay, and then we have the input voltage here through this divider, and it's going into input voltage is here at the B1 of the ADC, which will be channel 9 in our case. Okay, so we can move this over, and this the example of the buck converter here. Okay, so we set it up with PWM of the microcontroller. We're going to use the F28069, so it's running at 90 megahertz. We'll give it a count of 450. That will give us a switching frequency of 100 kilohertz. It's 90 million divided by 450 here, and since we're using ramp up ramp down, you have to divide it by another factor of 2, so the switching frequency will be 100 kilohertz. Okay, also in here we've got the current measurement op amp being simulated. It has a gain of 20, which we can see if we look at the data sheets on this of that in operation amplifier, and it has a gain of 20 volts per volt. Okay, so 20. Then we have this buck converter itself. Okay, and we could see from the schematic we had a 10 microfarad inductance, and 10 microhenry inductance here. There were two 330 microfarad capacitors, which we can pull out again. We can see that here we've got two capacitors which are 330 microfarads each, electrolytics, and we've got three tantalum capacitors here which are the same as the input capacitors here, which are 22 microfarads each. So we're representing this with a first capacitor 660 to two 330s in parallel, and then the second capacitor type, which is the ceramic type, is 22 microfarads, and there's three in parallel there. We've got the incapacitance represented here, and we've got the MOSFETs represented here, which we can see from the okay, so this is the data sheet for that synchronous FET, and we can see here that when we expand this, that we have for the main FET we have a 5 milliohm RDS on, and the synchronous FET a 1.1 milliohm RDS on, and we've put that in here. This is the diode synchronous FET, this is the on-state resistance, and the on-state resistance for the main switch. Okay, so we can do a simulation of this, and what we're doing here is we've got the tool to design the buck converter, to design the compensator coefficients. What we're getting out of here, we've put in a 8 kilohertz bandwidth, gain crossover frequency, and all the parameters for the buck. Okay, and we're getting these poles and zeros coming out, which is giving us our S coefficients and our Z coefficients. What we're also doing is we're exporting these to a file here. Okay, then here we have the control of the buck converter. So we go inside the control and we look at the compensator, and we're using the Z coefficients from the same file. Those coefficients for the controller will give us the control. We have the on-off switch here. We have a green LED here simulated, which will simulate any fault in the background here. We have different fault measurements. We have a hysteretic window comparator, which will monitor the output voltage, both upper and lower limits. The input voltage also cannot exceed a lower input voltage, and there is also control on the regulation of the converter. And here we have a soft start control, which we saw here in the soft start phase. Okay, so now we're doing a simulation of this. So we had a load step here, which is emulating the step of the load on the actual TI experimenting kit, which is the workshop kit, the digital power training kit. This is the base load on that kit, and then we have an active load where we can go up to above 2 amps. Okay, here we drop the input voltage in response to the input voltage drop. Again, we'll increase the input voltage shortly. So now we've finished that simulation. We can see the results here of the output voltage on a load step, increasing the load, a step on the input voltage, and turning off the load again. The entire digital control is simulated, including in the gray blocks the peripherals inside the C2000 microcontroller. We've got the ADCs here, the 12-bit ADCs. We've got the comparator DAC being simulated here. This is in the voltage mode control as we're simulating here. This is being used only for protection of the buck converter itself on overloads. The EPWM is being simulated as we've said here, including the digital comparator. And the voltage dividers are here. Note that from the schematic, these values are different to the schematic on the output voltage particularly, and also the current sensor. These are different values. Okay, so that's the first step. Let me go to another video to show a second step.